Okay, so in this lecture I will do some examples on Borel measures. So the notes will be essentially from this book by Walter, Real and Complex Answers by Walter Rodin. So all the 4 chapters will be from this book. So I will start with second example. We have already done example number 1. For this, let X be a locally compact Hausdorff space and let P belongs to X. Define lambda from CCX to C. Why? Lambda P from while lambda P at F equal to F of P for every F belongs to CCX. Yes, you can check that gamma P is obviously a linear function. This is trivial and also positive. Then lambda P is a positive linear functional on CCX. So we have now a positive linear functions on CCX. So we can appeal to reiszrepresentation theorem. Thus, why reiszrepresentation theorem there exists a positive Borel measure we wrote it by mu P on X such that lambda P at F is given by integral X F d mu. This is for every F belongs to CCX. So we get measure mu P. This we claim that mu P is the unit mass concentrated at P. This definition you have already done in your course on measure theory, advanced real analysis in second semester. Unit mass concentrated at P, which is given by, I will give the definition, which is given by mu P at E equal to 1 if P belongs to E and 0 if P does not belong to E. This, the definition of unit mass measure. So actually let's check how it is unit mass measure. We'll check it. Actually mu P at E you know, this measure mu p is given by integral over x function of e d mu. This you know from your course on measure theory. You have done this type of things. And now this integral x chi e d mu, you can write f is here as function of e. So you can write it as function of e. As function of e. So by definition, lambda p at f equal to f of p. So this you can write as as function of e at p. As function of f at p. Correct? And you know by definition of function, what you will get here? See, if p belongs to e, then it is 1, otherwise 0. It is 1 if p belongs to e, otherwise 0 if p does not belong to e. So we have proved that mu p is a unit mass concentrated at p. Okay, I think you might have understood it. Let's come to example number 3. One measure consider let x equal to n, the set of natural numbers. Then Cx is equal to all complex valued sequences. Complex valued sequences. All complex valued sequences. How it will be? We'll check it. From here, what you get? All f from n to c. So, you know, if a sequence is a function from n to c, so f is a sequence. And you know, when it is a discrete space with discrete topology. So you know every map from n to c, here it is Euclidean topology, here it is discrete topology, and you know that every map from n to c will be continuous. Means, what I mean here, every sequence from on n, any complex value sequence will be continuous. So it means it includes all the complex valued sequences. So that's why I am not writing it there as a continuous, because it will include all sequences. Because we are taking n as discrete space, discrete topological space. Okay, and with the discrete topology. So also another term we encounter is CCX. Encounter is CCX and CCX. Means all complex valued sequences, all complex valued sequences, all complex valued sequences. Listen, what are you saying? All complex valued sequences, such that support of f is compact. Support of f is subset of n. N is with discrete topology. What it means? Support of f is compact. Compact will implies support is finite. support F is finite. You know that in a topological space, a subset, in a discrete topological space, subset is compact if and only if it is finite. This you have done in the course of topology in second semester, so you know it very well. Okay, all complex, and what we should have, we have all complex valued sequences with only finitely many non-zero entries, finitely many non-zeros entries. Okay, finitely many non-zero entries. Okay, so we have CX, we have CCX. Okay, so we'll define a map. Define lambda from CCX, I mean CCN, X is n, to C Y lambda of F equal to summation n from 1 to infinity F of n for every F belongs to CCX. Also, obviously lambda is linear, linear. You can check it easily, just like C. Lambda is linear. Why? Lambda of alpha F plus beta G is the same as n from 1 to infinity alpha F plus beta G at n. It is trivial, but I am proving it. N from 1 to infinity alpha F of n plus beta summation n from 1 to infinity G of n, and this value is equal to alpha times lambda of F plus beta times lambda of G. So it is a linear. Also, obviously positive. If F is greater than 0, lambda F is also positive. If F is, lambda F is also greater than 0. So we get that lambda F is a positive linear functional. Is a positive linear functional. So again you get a positive linear. So again you can appeal to reiszrepresentation theorem. Okay, thus by reiszrepresentation theorem, there exists a positive measure I mean Borel measure mu, we denote it by mu on X such that lambda of F, you know the statement of reiszrepresentation theorem, integral over n, X here is n, F d mu, means mu on n, I mean the X here is n, for every F belongs to CCX. So this we have. Okay. So this for every F belongs to CX. So this is why reiszrepresentation theorem. Okay. So we again got a measure mu, and in this case mu, we check that it will be a counting measure. Now we check that mu is a counting measure. You also know the counting measure, definition of counting measure. on X series N. For this, let E be a subset of N. Correct? Then we check that mu is a counting measure. Let E belongs to E subset of N. Then again same technique, measure of E. You know that this is given by integral over N Kerr's function of E d mu, and by definition of lambda you will get it is equal to lambda of Kerr's function of E. Correct? And again by definition of lambda, how we define here, see here, this one, okay. You will get here summation n from 1 to infinity Kerr's function of E at n. Kerr's function of E at n. So, you know, when n belongs to E, it is 1, otherwise 0. So, it will Kerr's function of E1 means chi when 1 belongs to E. So, what do you get here? E subset of n. Okay. So, what will it will be all the elements of E when E is a finite set, and infinity if E is infinite set. It means cardinality of E, number of elements of E, if E is finite, and infinity if E is infinite. Correct? We have this one. So we have done this second example also. You understand all the things. First case, it was a unit mass measure concentrated at P. So in this case, we have counting measure. So we come to one exercise which I will prove here. Exercise. This is related to example number 2. Let XVA, again locally compact, Hausdorff space, and P belongs to X. Let lambda P from CCX to C we defined by lambda P at F equal to F of P for all F belongs to CCX. Correct? Then show that, then what we have, then question is, then show that lambda P at F is equal to integral X F d mu for every F belongs to CCX. Put this as equation 1. If and only if this, then show that lambda Pf equal to integral X F d mu. If and only if and only if mu equal to mu P. Mu P क्या है? What is mu P? You know, unit mass measure mass concentrated at P. So we'll prove it with this exercise. First is, suppose solution of this exercise. First, if mu equal to mu P, if mu equal to mu means mu is the unit mass concentrated at P. You know, P Singleton set, outside, all the mu is concentrated at P, so we get F defined only on P. So rest it will be 0, complement of P it will be, function will be 0. So then clearly F belongs to CCX. And integral over x f d mu, this value equal to integral, you break it in singleton P f d mu plus x minus singleton P f d mu. So since your mu is considered P, so this term will be 0. So what you get here? F of P, because mu of x minus singleton P, base of this set, is 0. And so this integral will be 0. So you have, by definition, this is nothing but lambda P at F. So you have proved this way. Equation 1. If mu is unit mass concentrated at P, so we have proved that lambda P at F is given by integral x f d mu. It means equation 1 is proved. Now we take converse part. Conversely, suppose conversely, to show that mu satisfying this equation 1, I mean this equal to, I will show you here, satisfying one this equation, this one, satisfying 1 must be mu equal to mu P. We have to show that mu of V is 0 for every open set such that P is not an element of B. Okay, so we in the set where P does not belong, that set has measure 0. This we have to prove. Since mu is inner regular, for open sets, that is property of representation theorem, mu of V is equal to supremum over mu K such that K is subset of V, K is compact. K is compact. This is what we do here. We take V and we want to find the measure V. What will take? We take V and take all compact subsets of V. So when we take measure of those compact sets and we pick max supremum of that will give the measure of V. This is called inner regular property of measure mu. So from here what we get? For every epsilon greater than 0, there exists a compact set K containing V. There is a compact set K containing V such that such that what you have, mu of V minus epsilon is less than mu of K. This concepts are real, so you can do this. Okay. K is compact, and we can appeal to Jurgen's lemma. By Jurgen's lemma, okay, then by Jurgen's lemma, then by Jurgen's lemma, there means there exists f in CCX such that f of x equal to 1 for all x belongs to K, and support of f is contained in V. Okay. Now this will imply that mu of compact set K is less than or equal to integral of x d mu. Because K, I'll tell you, because K is subset of, as K is subset of x, so mu of K will always be less than or equal to, means you can write as K, integral of K, gets function of have d mu. Okay. Here mu of K is subset of x, so mu of K will always be less than or equal to integral over x f d mu. Okay. Always less than or equal to f d mu, and this value is equal to lambda. Okay, you have this definition, lambda p at f, you have defined it like this, and this value is equal to f of p, because p does not belong to p, and support of f is contained. Okay, this you have. So what you get here, and this value is equal to 0. This value equal to 0. Why this? Because B does not belong to V, and support of f is contained in V. So what you get? This implies mu of compact set K is equal to 0. It's okay. So let's put this equation as second equation. So what you get? From equation, we have done equation second and put this third. From equation third and second and third, what do you get? What you can say? Then from second and third equation, we get mu of V less than epsilon. And since epsilon greater than 0 is arbitrary, and since epsilon greater than 0 was arbitrary, so we get mu of V equal to 0. So we have shown that mu of V equal to 0. Now we want to show that mu is concentrated at P and P belongs to X. Since singleton P, you know, P is compact or closed and closed, so X minus P will be open. So instead of V, we take X minus P. Now take V equal to X minus singleton P. So this is also an open set, and we conclude that mu equal to mu P.